everyone. So my name is Addy. I'm a graduate student at MIT.
And my name is Jesse, another fellow graduate student in the same department.
Yeah. I guess today we're part of the MIT electric vehicle team. We're a student team on campus that designs and builds electric vehicles. And recently we have started designing and building hydrogen-powered vehicles. So we wanted to tell you a little bit about our work and some cool and fun things we found. Yeah. Next slide, please.
Yeah, so here we just wanted to give a general update for the progress that we've had since our last showcase at the Hydrogen America Summit in the States, and show some of the work that we've done on our vehicle. And for people who aren't used to that space, it's going to be very obvious to a lot of people who work in the vehicle development side of things, but we thought it was still pretty interesting to talk about regardless. Next slide, please. Yeah, so this is the our bike Toothless, named after the dragon from one of our favorite movies. And as you can see, it's very simple in like general construction. It's a fuel cell operated bike that functions as sort of a range extender with a swappable hydrogen tank in the back that has about 10 liters of hydrogen stored at 350 bar. We have an electric motor that can run at a peak torque of 110 Newton meters with a 34 kilowatt peak output, and a kind of buffer energy storage system for a 32 amp hour lithium battery that operates at 50 volts. And we also have an energy management system that we'll talk about more later, but a key part of it is that it has a DC to DC converter and can help control the flow between the fuel cell and the battery and the motor. Next slide, please.
Next slide, please. Yeah, so this is just like a brief image of the bike. We actually have it. It will be here at 3 p.m., hopefully. It got stuck in customs, but it's on its way. So if you are interested, we'll be over at both C159, so please come check it out. It's quite a cool little device. Can I get the next slide, please? Yeah, so I'm just talking a little bit about like how the system works and some things we found while we were building the system. So we have a 1.5 kilowatt fuel cell, a motor, an isolator, a battery, and an inverter. And together, these components make up the main powertrain of the system. The battery makes up the high power components, so that deals with a lot of the high transient response and the high power during acceleration phases of the vehicle. And the fuel cell is kind of there as you can think of it as a trickle charger. It recharges the battery as we go. So one of the things we were interested in is like, how big a fuel cell do you need to put on a hydrogen vehicle? Does it need to be huge? Does it need to be small? So we ran some initial tests with it. Can I get the next slide, please? Can I get the next slide, please? Oh, thank you. Sorry, we're having a bit of technical difficulties with this presentation, but it's all good. So what we started with was defining, for those of you who are unfamiliar with the vehicle testing space and how we develop vehicles in the alternative energy space, one of the concepts we use to compare range across various vehicles is called a drive cycle. So essentially, like if you want to compare a gasoline-powered vehicle, if you want to compare a hydrogen-powered vehicle to a battery-powered vehicle, we need a scientific standard of comparison to make sure when we're testing for range, they all have like the same environment. Like just driving it around a city doesn't always work, So we defined, this is the MIT pretend motorcycle drive cycle. This is a fake drive cycle, but we're working on validating our system on like more scientifically standardized drive cycles in the future. But this is a fairly aggressive drive cycle with a 90 kilometer per hour peak and an acceleration of 13 meters per second squared. Can I get the next slide, please? 13 meters per second squared is actually quite an aggressive acceleration. For those of you who are unfamiliar with vehicle performance specifications, that's about a 0 to 100 kph time of 2 seconds. So that's a really aggressive acceleration. And one of the reasons we were doing this is because and we were trying to, I don't know if you guys have seen For's Hydrogen Racing is here, and there's a couple of other student teams who are looking into like hydrogen for the racing aspect. There's not a lot of people at like the industry level or even like the racing level that are looking into like high performance hydrogen vehicles. How do we use it to like in situations like racing? And you might ask, okay, so why are we looking at racing? What is the point? And I don't think our team necessarily, we're looking at racing for racing's sake. It is cool, of course, and produces a lot of excitement. But when you take a vehicle and you throw it at a track, things like Formula One and other kinds of motorsport have taught us, it provides a set of very interesting problems to push the system like to limits that you don't push it to in like the real world. And in those limits, you learn a lot of things about how to develop a system, which is one of the motivations for looking at racing. And a lot of inventions on like modern vehicle technology have come out of racing, things like Formula One and that kind of stuff, which is a reason you look at racing as an application as opposed to doing racing for racing's sake. Can I get the next slide, please? Thank you. Yeah, so here's our some initial data from our experiment. So these are two curves. The lower one is just on the battery and the upper one is with the fuel cell. So what we found is that a really small fuel cell, even on a motorcycle, it's a 1.5 kilowatt fuel cell, which is not a lot, still maintains the charge of the battery. While, of course, when you don't have a fuel cell, the battery discharges. And this was interesting to us because it told us, well, the motorcycle actually uses in steady state, even at a very aggressive drive cycle, far less power than we think it does, which means for applications on high performance vehicles, we maybe don't need that big a fuel cell when we're talking about these kind of systems. Can I get the next slide, please? So this is a proof of the law of conservation of energy, so we can actually skip it. Next slide, please. Thank you. Yes. So one of the techniques we were using when we were comparing systems, especially developing vehicles, simulation is very, very heavily used across industry and research to compare all sorts of energy management, algorithms, like all this kind of stuff. One of the things we have always been, like our philosophy as a team and inside of research and engineering, simulation is great, but there comes a point where you have to put stuff on hardware because hardware is where it's real. Hardware is where we get data that works in the real world. And some of the questions, like that's how you know your simulation is accurate. And so one of the questions for us was, how do we do this without having to build like an entire vehicle every single time we need to compare stuff? So one of the key aspects that we were comparing was this idea of energy management system algorithms. So what is the best algorithm for various types of comparing, like sharing power between the fuel cell and the battery and other components in the system? So what we're working on right now is this open source small scale energy management system. So this is a 1.5 kilowatt DC-DC converter with a microcontroller on it. It's an STM32. And what we can do with this is we can hook up a hardware source of any kind. So that could be a battery, that could be an engine, that could be a fuel cell of any size. We hook it up to the DC-DC converter. So there's two inputs. So you can hook up a battery and a fuel cell. You can hook up a battery and a battery. You can hook up a supercapacitor bank and a fuel cell, whatever you want. And we can put it into either a simulated or a real load. So a simulated load could be like a DC electronic power supply. A real load could be our motorcycle on the dynamometer that we showed you earlier. Or a real load could be our motorcycle on the track, which is another thing that we've done. So this power converter fits in the lab scale. It also fits in a physical platform on the actual vehicle, which allows us to get data in the real world and allows us to get data in the lab. So this is our kind of concept for how we want to be testing energy management algorithms in the future, because it kind of removes that uncertainty of simulation aspect, and it gives us a standard of comparison when we're comparing various different algorithms on the same hardware system. So when we compare performance metrics, instead of comparing them across papers or data taken in academic research across different platforms and different simulations, this is a better standard of comparison because we can compare them all across the same ground truth. Can I get the next slide, please? Yeah, so we've learned a couple things. We want to share them with you, and then we want to tell you where we're going as a team and the kind of support we're looking for and why we're at World Hydrogen Summit. So the first thing I think we learned was really important, that this project was like a fantastic hands-on learning opportunity for students. You know, like building a hydrogen-powered vehicle is like a ridiculously complex system. You have power electronics, you have controls, you have this chemical energy conversion that needs to happen, especially when you're doing fuel cell stuff. And this kind of produces a really cool fusion of people at the undergraduate level. Like we have chemies, we have material scientists, we have electrical engineers, and there aren't that many project teams that really produce that level of fusion at the undergrad level. So this is one of the things, like when we're talking to people here and we're talking to other universities, how can we implement these kind of programs at other universities to provide hands-on educational opportunities for undergraduate students, high schoolers, and especially from those coming from like previously underserved populations and underrepresented minorities. There's a lot of studies that indicate that hands-on education really increases the viability of career trajectories for underrepresented minorities. Coming from like backgrounds with no hands-on education to hands-on education, it really like provides better learning pathways. And the second is a little bit what I talked about earlier in terms of like how a platform like this is great for full system testing and to provide us a ground truth for data. So can I get the next slide, please? Yeah, so our goals moving forward, like as I said, we would love to kind of work with anybody who's interested in providing hands-on educational opportunities for students, either the high school level, undergraduate level, learning about like clean energy, and how they can how their work can make an impact in industries like the spheres of hydrogen, but also like spheres outside hydrogen. What you learn from these kind of projects can translate very well to like other spaces of energy, especially if you're interested in making an impact. We are also starting to build a second version of our bike. This was very much a proof of concept bike. It was a fuel cell. We just shoved it on an electric bike and we drove it around. We tried to figure out what would happen and we learned some things. The second version of our bike is going to be an optimized performance tuned system designed to compete head to head with a gasoline powered vehicle. So if anybody is interested in partnering in that kind of a project, we are looking for partners and we're very open to working with anybody. On the next slide, I described some challenges. No, sorry, next slide. Our current biggest challenges as a team with building this high performance vehicle, one, storage. It turns out for 5 gallons of gasoline, you need about 90 liters of hydrogen compressed at 700 bar. And 90 liters is about the volume of an entire motorcycle. So that's not really going to work super well. So if anybody has experience in liquid hydrogen storage, LOHCs, metal hydride, we'd love to talk to you because we have a problem and we really need to fix it. The second is thermal systems. Our team doesn't have that much experience with thermal systems and trying to manage how do we package the thermal system to compare recycle the energy from various parts, manufacturing in those areas, and the balance of plant of the actual fuel cell. And the third is transient response of high DPDT systems. And what I mean by that is in racing vehicles, it's not just peak power that matters, it's the rate at which the power can be delivered from the fuel cell to the actual motor that also matters a lot, which is what I mean when I say a high DPDT system, which is different than conventional road vehicles where the power matters, but how fast it gets delivered doesn't actually matter that much, which is another really key challenge in racing vehicles that can produce a lot of innovations in the vehicle design space. So if anybody has experience in that area, that's something we're also really interested in exploring. I think I have that. I think one more slide and then we're done. I just wanted to thank okay, wait, can I get the last slide because I need to thank somebody really quick. Huge thank you to Air France, KLM, Martin Air Cargo, who flew our bike over here for free for us. So I just want to give them a shout out because they're amazing and they're wonderful. So thank you, Air France. Thank you all for your time. Please come talk to us. We'll be over there.
Thank you for your time, everyone.